see right up here a definition of vectors. Right? Definition of vectors is they are a quantity that has direction and magnitude. So I'm just going to write direction and magnitude.
So what section is it?
Don't worry about the section. It's in the trig book. It's chapter 8. Okay? I'm not really teaching it according to the sections. I'm giving you an overview of vectors in 2 days. All right? So it has direction and magnitude. That's what we're looking at. What's direction? Well, if you look at these arrows that I've drawn over here, these arrows have direction. And they start at an initial point and they move in a direction. The arrow shows which direction they go. So you can see that each one of these has a little arrow at the end of it, and that tells you it's going in this direction. From the initial point to the point at the end of the arrow. That is the direction of the vector. Now we could describe that direction by an angle. We're not going to do that at the moment. We're not going to get to that today. That's something that I could talk about in a future lesson on vectors, but we're not going to do that right now. Okay, but just know that a vector has direction and magnitude. We'll talk about magnitude in a little bit. A vector has what we call an initial point. This is the point where it starts. So looking at this grid up here, we have a red vector. What is the initial point of the red vector?
0.
Huh?
0.
How do we describe that point?
0, 0.
0, 0, also known as
Origin.
the origin. 0, 0. Okay, what's the initial point of our green vector?
1, 5.
1, 5. That was you, Baruch, right? Trying to get bonus points in the last day? All right. 1, 5. And our blue vector. Lucas, what's our blue vector's initial point?
5, 4.
5, 4. Correct. So 5, 4. What's the terminal point? This is where it does what? What do you think? If we have an initial point, it's where it starts. What do you think the terminal point is?
The arrow.
Where it ends.
Where it ends. Thank you. And Fiona, yes, you're right, but I was looking for a different way of describing it. All right, what is the terminal point for our red vector?
2, 1.
2, 1. Over 2, up 1 is the point. 2.
How can we say it ends? I mean, it's like continuous, right?
No, well, technically the vector only brings you so far. So
what's the use of the arrow?
The arrow tells you that if you multiply this vector more, it could keep up. But again, a vector only has a certain magnitude that tells you how far it goes. The arrow is showing you the direction of the vector. In other words, if I had the arrow on this end, that would mean this was the initial and this was the terminal. It's telling you that it's proceeding from this point to this one. That's what the arrow is telling you. Okay? And yes, we could continue a line along this vector. And if you take calculus to advanced levels, you'll learn how to do parametric equations of a line. And if you use this vector, then depending on how you use it, your equation will start at this point and it will go in this direction. And you would have to go to negative values to go the other direction. And the same would be true for this point. Going this direction, negative values will take you this direction. We're not going there yet. Okay? Again, that's for a calculus class discussion. All right. So then where does our green vector end? Where's its terminal point?
3, 2.
3, 2. Over 3, up 2. And Tim, how about the blue one?
3, 6.
3, 6. Now, what we want to do is we want to figure out a way to describe the vector itself. Vectors, we're not going to describe everything about the vector, but a vector can be described as an ordered pair. Now, what do I mean? It's not it's not per se an ordered pair like a point. This is a point, right? But we can put a vector in ordered pair notation. Different books use different symbolism for that. And if you're on computer software, like you might be if you take calculus to a multivariable calculus level, which is calculus 3 and 4, those kind of classes, you'll do a lot of work through computer software. And the computer actually writes the vector just like this, depending on the software you're using. Some software will do that. We're going to use, for this class, we're going to use this notation. That's going to be our vector notation, and we'll put a comma in between. Okay? So instead of a regular parentheses, it's these kind of V-shaped ones. I didn't mean to make them quite so sharp. You do it more like this. That looks a little better. It looks the same, but it's not quite so sharp. Okay? This is a way of notating a vector in ordered pair form. Now, what does ordered pair form tell us? The way we find this form of the vector is to take and do one of these operations. In particular, we're going to use this operation here. We're going to take the initial point and subtract it from the terminal point. So it'll be the terminal point minus the initial point. Right?
So it's like a slope.
It's very much like a slope. Yeah. Except instead of being change in y over change in x, which comes first in this notation?
The x.
The x comes first. And instead of being set up as a fraction, we've set it up as an ordered pair. But it's very, very similar, very related to a slope. And that's why we can use a vector to describe a line later on when we get to parametric equations. And again, I'm not going to show you what those are, except to tell you that a parametric equation gives you one little equation for the x value, and then another one for the y value. And that's why we can use this vector with it. Okay? Alright, so knowing this, I want you guys to tell me what my three vectors are, how to describe these three vectors. The red, the green, and the blue. How about the red? Serena, can you tell me what would be the numbers that I would put here for the red? How do I get it?
Minus the minus 1.
Terminal minus initial. Which one's the terminal?
It's 2, 1.
2, 1. So, minus 2 minus 1? Are you sure about that?
No, I said 2 minus 0 and like.
Oh, 2 minus 0 and 1 minus 0?
Is that what you say?
Okay, yes, I misunderstood you. Sorry. So 2 minus 0, 1 minus 0, and what does that give me?
2, 1.
2, 1. So, oops, I should use the right color, shouldn't I? So this vector is 2, 1. How about our green vector? James, what's the green? Huh?
0. No, green.
The green vector.
1. Which one? 3, 2.
No, what? How? Remember, you can
Oh.
describe it by the terminal point minus the initial.
2, 3.
Terminal point minus the initial.
2 minus 3.
Terminal point minus the initial. Baruch, you're right, but let James get it. Terminal point minus
1, yeah. 2, negative 3.
2 and negative 3. All right. 2, negative 3.
Huh?
And Tim, how about the blue?
Oh, negative 2, 2.
Yeah, negative 2 and 2. All right. So this is a way we could describe each of these vectors. And if you look, what this tells you is the vector takes you 2 points in the positive direction on the x, and then one more unit positive on the y. 2, 1. Very much like a slope, as Baruch said. All right, in this case, we started up here. It's going to take us 2 on the x, positive 2, and negative 3 on the y. If we use that vector again, what point will we end up with? We started, so let's say we've started up here and we went down here. Now what if we use that vector again? What point will it bring us to from here?
5 minus 1?
5, negative 1, exactly. If you were to continue that vector again, it would bring you down to there. All right? We'll come back to that in just a moment when we get here. Now, last one, negative 2, 2. We go back 2 and up 2. If it would have been negative 2, where would this have taken us to? What point?
Down
Yeah, tell me the point.
there. 3, 2.
3, 2, it would have taken us right to there, just like the green one. Okay, but from a totally different starting point. All right. So this is a little bit of how vectors work. Let's see. Addition and subtraction of vectors. One of the things, there are a number of operations that we can do with vectors. Okay, you can add them up, and that's useful for figuring out the cumulative force that might be applied. For instance, in physics, how many of you have talked about force in physics class? Did you use vectors to describe the direction of the force?
Yeah.
Okay. And so if you have two different things going together, you haven't taken physics yet, have you?
What?
You've taken it this year. Some of the rest of you, I know you've taken it already because you came from other schools. But James, you've been here since you were a freshman. Unless you took it as an 8th grader.
I feel like I did.
You think you did? Maybe you did.
It's physical science.
Okay. So, anyway, James's memory is apparently glitching on him, but we'll forgive him for that. Okay, if you've got these two, let's say that you have an object, and these two vectors were both pushing on that object at the same time. Okay, and we wanted to figure out where that would leave the object. You've got one that's pushing down 3 and over 2, and one that's pushing over 2 and up 1. Well, the way to do that would be to add the vectors together. So if you want to figure out the total result from pushing the red vector plus the green, you simply add them together. It's going to be 2, 1 plus 2, negative 3. And what does that give me? 2 plus 2? 4. 1 plus negative 3? Negative 2. And that gives me my new vector. That would be the result of the red plus green. Alright, so we'll just highlight that with some green so that you can see that that's the answer. That's addition. Now what if I was going to take the exact opposite force of this red vector and push on this object at the same time as this green vector is pushing on the object? How would I do that? I want to push on the object with the opposite of the red force. Think about it. 1, 2 would go here to here. Is that opposite of this?
That would be 0, 0.
It's a reflection of it.
0, 0 takes me nowhere. The opposite of 2, 1 would be negative 2, negative 1. And it would take me this direction. Do you see what I mean? It takes me the exact opposite direction. So if I wanted to see what would happen if I combined the green with the opposite of the green, or with the opposite of the red, then what I would do instead would be the green minus the red. Think about that. It would give you 3, oops, I'm sorry, that would be at 2. 2, comma, negative 3, minus 2, 1. Distribute this across, what's it really become? It's like adding
Minus 2 minus
You don't have to do that distributed step when you're doing the math, but you can see how it works. By subtracting, I basically made this the opposite direction of the original. Now, I'll tell you something interesting about that tomorrow, I think, when we get to that. Yeah, that'll be tomorrow, we'll get to that. But when you look at this, now we've got, what's our green minus red? What's the result? 2,
0.
0, -4. So if you put these two together like that, and let's say we started at this point with both of these vectors, the positive green and the negative red, we're not going to go this way at all. We're just going to go straight down 4. Okay? If we try to put those together. Now, there is a whole lot more we can go into with vectors, and that's not my job today. I just want to get you a little bit comfortable with the idea of vectors so that you don't do what happened to me when I went to my college classes. I go to my college classes in math, and suddenly, I said, nobody told me this. I took linear algebra. If you have to take linear algebra in your course of study, don't take it till you've taken some other upper level math classes. Don't take it right after Calculus 1. It's a bad idea. Okay, I got through the class, but it just about killed me. So you want to take it a little bit later, because linear algebra works with vectors all the time. It's pretty much your whole course. It's easier to take it after you take vector calculus, which would be calculus 3 and 4. And if you do it after that, boy, it makes a whole lot more sense. What was that, James?
Calculus 3 and 4.
Calculus 3 and 4 is kind of fun because you get to play with computers. If you take a multivariable calculus course, they do it all through computers. It's actually not so bad. You scratch your head when they get to a couple concepts, but it's not too bad. All right, so that is addition and subtraction of matrices. Does that make sense? Okay. Scalar multiples. This should be super easy. How many of you have worked with matrices?
What?
Matrix?
A matrix. How many of you have worked with a matrix? Not the movie, but matrix algebra and stuff like that. All right. Some of you have. All right. Do you remember, Tim, maybe I'll remind you, matrices, you would be looking at stuff like 2, 1, 3, 4, you know, and you have a 2 out in front. What does this mean? Yeah, you just multiply everything in there by 2, right? So you get 4, 2, 6, 8. All right, that's all it is. Well, scalar multiples with vectors is the same deal. I'll underline this so it's a little clearer. Our scalar multiples with vectors are exactly the same. So let's say we wanted to go 2 times the green. Well, gee, how do we do that? You take the green and you multiply everything inside by 2. So you get 4, -6. That was easy. And basically, do you see this drawing we did over here?
Switch.
That's it. This drawing with this dotted line going down to here, that was 2 times the green.
Will this be true if we multiply 2 by the initial and the terminal, and then we add it?
In other words, if we multiply the initial point by 2 and then the terminal point by 2 and then add, and then do the subtraction, well, let's see. Okay? So let's take our initial point, we'll multiply it by 2, we get 2, 10. Let's take our terminal point, we multiply it by 2, we get 6, 4. We subtract, and you get 4, -6. Did it work? Yeah. Same result. Same result. So yes, but it works that way. All right. Let's see. So that would be the green. Do you think we could do a scalar multiple of the red plus green? Yeah, it's a vector now. It's a new vector of this. You just multiply it by whatever scalar. Okay? So before we get on to this concept of, you can see that these get different lengths when you multiply the vector by a certain coefficient or scalar multiple, you'll call it. When you do that, you get a different length vector than the original. Is it in the same direction as the original?
Yeah.
Yeah, it is. What if we put it by a -2? Now what happens? Instead of this, it's -4, +6.
Opposite.
goes in the opposite direction. Just for your information, tomorrow we're going to look at this more. We still call those parallel vectors. Alright? Still call them parallel vectors, even though they're heading in opposite direction. If you put them on a point, one's pointing this way, the other's going that way. We still call them parallel. So just so you know that, tomorrow we will work with that. Alright, and what else? Magnitude and unit vectors. Now, unit vectors is going to emerge out of both magnitude and scalar multiples. So let's figure out magnitude first. When we say magnitude, what are we discussing?
Big or small. Big or small.
Big or small. The size of the vector. Which of these vectors has the smallest magnitude?
Red.
The red. You can tell by looking at it, can't you? Which one's the largest?
Green.
Green. All right. So we can pretty easily tell magnitude of the vector, generally speaking, by looking at it. This one is probably greater than what? Greater than how many units?
2.
Greater than 2, but probably less than
3.
3. This one is greater than
3. No, 2.
greater than 2.
Less than 3.
It could be less than 3. Yeah. And if you know your geometry really well, you can figure that one out super quick.
Yeah.
Okay? And this one, well, it's greater than 3, isn't it? But it's less than, probably less than 4. Looks like it could be. It might not be. Well, let's find it out exactly. I have a question for you. What is this shape right here, if I take this?
Right
Triangle. Right triangle.
It's a right triangle. You could use the Pythagorean theorem to come up with your magnitude. Now, if we were doing this, the way we would do it in notation, and if you look in your book, they'll show you this, the way we come up with magnitude is they use this notation. Magnitude of the green. And they'll put it in a double, it's like a double absolute value symbol. It's not an absolute value really, but it sort of is. My calculus professor actually called it he called it basically an absolute value. You could think of it that way, I suppose. I didn't find that to be the most helpful way to think about it, but so we could also talk about the magnitude of the red vector and the magnitude of the blue vector. Alright, so we have these 3 magnitudes. How do we find them?
Pythagorean.
You could use the Pythagorean theorem. I'm going to show you the way we typically do this and the notation we typically use when we're starting to work with vectors. Okay? We take the ordered pair form, which in this case was 2, -3, and what we do what we call a dot product. Now, you might be saying, what's a dot product?
Multiply.
It is a form of multiplication, and it's the form that we would use with vectors. And I shouldn't have written those so close, because now I don't have room to work. But basically it's this. If you have vector A, vector B, dotted with itself, AB, the dot product is going to multiply this term by this term, and you'll get A squared. And you will add to that this term times this term, B squared.
Oh, so there won't be any food vector squaring and all.
No, there won't be anything, no, it's not like that, correct. It's not like foiling. Okay? So this is a little different. If you look at this though, what we're really saying, oh, and the other thing we do is we put this in a square root. I almost forgot that.
Oh.
That would have been an important detail to forget. That would have messed everything up. If you think about this, we're saying the magnitude of this is equal to a squared plus b squared. Wait a second, where does that look familiar?
Yeah.
Distance formula, that's one place. Where's another place that looks familiar?
Slope.
Pythagorean theorem. Yeah, because isn't that what c equals? So really we're treating this like c. Okay? So knowing that, let's do this operation with this green vector. So the magnitude of the green is equal to 2 times 2, which is 4, plus negative 3 times negative 3, that's 9, all in square root. Square root 13. Does anybody have a calculator super handy to crunch that number for us? Obviously, it's less than 4, greater than 3. 3.6 approximately?
3.60.
Give me 3 decimals.
3.605.
0.5. 3.6. Did you round this last one?
No.
Should it round up or down? Is 5,
5, 5.
5, 5, so it round up. 3.606. Okay, so that is the magnitude of the green. And if you were to put this and lay it flat on the grid, you would see it would go down to about there. Okay, because it's 3.606 units long. That's the magnitude of this green vector. You could do the same math here. If you did, you would come up with, let's see, this is, that's going to be root 5. Okay? So the red, by the same method, you go 2, 1, dotted with itself, and you're going to get root 5. And if you do the same thing up here, I like to use right triangle geometry whenever I can. This is 2, 2, isn't that going to be 2 root 2? Because it's a 45, 45, 90 triangle.
Yeah.
So this is just going to be 2 root 2. Okay? So our blue has a magnitude of 2 root 2. All right. So that is magnitude of vectors, and it appears I did not leave myself enough room to work down here. But the last thing is unit vector. How do we come up with a unit vector? What is a unit vector? So let's see if we can come up with a definition. Now, I want you to think about that word unit. Huh? Unit, 1. 1 unit, right? What's a unit circle?
Radius of 1.
A circle with a radius of 1 unit. So what do you think a unit vector is?
1.
Huh?
What?
The
1.
it's a
Magnitude
vector that's
1?
1, 1.
Right. Magnitude equals 1. That's a unit vector. Magnitude equals 1. So let's find our unit green vector. Unit green. How do you think you could find the unit green vector? How do you find the unit green vector?
Make a circle. 1. That's already.
Well, I've got a question. If you divide something by itself, what do you get?
1.
1.
Okay, 1. So if you divide a vector by its own magnitude, what magnitude will you get? 1. Make sense? So really, the unit green would be this. You take the green vector and you divide it by the magnitude of the green vector. Make sense? So we take 2, negative 3, and we divide it by that magnitude, which is root 13. And that would give us the vector 2 root 13, comma, negative 3 root 13. And that vector,
We're dividing.
Wait, this is multiply.
whoops, I'm sorry. Thank you guys. I'd love to say that I did that just to see if you were paying attention and not falling asleep. But I can't say that because that'd be a lie. Alright, dividing it by that. Alright, and there you have a unit vector. Our textbook will use the letter U for unit vectors. Alright? So this is a summary of vectors and very basic things with vectors. So let's go through this again. Vectors have an initial point, which is where they,
Start.
a terminal point, which is where they,
And.
and if you want to find the value of the vector x, y values, you simply
Subtract.
subtract the initial from the
Terminal.
terminal. You can do which operations with these vectors? Addition, subtraction, and scalar multiples. You can also do what we call a dot product. We learned that over here with magnitude. Magnitude tells you what?
The.
You could think of it as length. That's an easy way for us to think about it. It's the length. Magnitude tells you length. Someone could get all technical with me about that, but I'm not too concerned. And a unit vector is a vector in which the magnitude equals 1. So you divide the vector by its magnitude.